I would be very glad to say several words about our institute and to present you main agenda of our institute. Probably you know that MEFI decided to change completely the structure in several years ago, actually 4 years ago. So instead of old departments or faculties, so MEFI is now composed of 5 or 6 institutes. And our institute was created as an attempt to extend the portfolio of MEFI toward biomedicine, to biomedical applications. So it looks unusual that MEFI, which is a nuclear research university, it's more associated with some power generation, but this is not true. Just to clearly illustrate how diverse is MEFI, so our institute, FISBio, or Institute of Engineering Physics for Biomedicine, was created. We work basically in the interface of engineering physics, chemistry, biochemistry, and biomedical technologies. So this is our task and how it was created. So just it was created, as I said, 4 years ago. The first acting director was Irina Zavistovskaya. Right now we have a new direction, but we continue the same let's say, project. So the basic idea was to combine education with some active research programs in order to, form students in this specific research environment. Finally, we would like to achieve leading positions, at least at in several fields of biomedical research and applications. Our institute, the chairman of FISBio is a famous Paras Prasad from State University of New York at Buffalo, the United States, who is actually the candidate for the Nobel Prize. We hope that he will get it one day. So our acting director is Alexander Garmash, who is here. We are well implanted because there are many clinics around MEFI and FISBio, including Blokhin Oncology Center and different clinics. So we are in a very good environment. The education of the institute implies 2 tracks. We want to finally have engineer physicists specialized in the area of biomedical technologies, or physicians specializing in, let's say, high-end technological approaches in biomedicine. So we have bachelor, we have master programs, and the structure of the FISBio is indicated here. Then if we look at the research program, so we try to combine the strongest points of MEFI with some new technologies. So basically, FISBio research agenda was formed in the interface of several research fields. So this is nanotechnology, biophotonics, nuclear medicine, and computer medicine. So, and in this interface, we just try to find some interesting new areas, exciting new areas. And one of main objectives of our research is the search of new methods how to detect or image cancer and treat it finally. So we work on therapies and diagnostics. And if we combine these 2 terms, we can say theranostics, which means therapy and diagnostics. Basically one of main interests is nuclear medicine, and here we are very well implanted, and people from this bio work in quite different directions of in nuclear medicine and in radiology. So right now, just one of main focuses, this is the use of nanotechnologies. That's why one of programs of these seminars is one of objectives of these seminars is to try to marry, let's say, technologies of nanomedicine and nuclear medicine and also radiology. So here the idea is the following. So here we talk about very small objects. It's nano objects. I mean, it's 10,000 times smaller, these objects, than the size of human hair, for example. So this is a very small objects, nano objects, which is nanometer, 10 to the power at minus 9 of meters. So, and there are very interesting properties of these nanomaterials at the nanoscale, new optical, new magnetic properties, etc. But what is important, if we cover these materials, I mean nanomaterials, by some biopolymers, they can travel in the bloodstream without any problem, but they still will concentrate in the region of tumor, because blood vessels are not well developed in the region of tumor. That's why we can have a natural accumulation, the so-called passive accumulation of nanoparticles in the region of tumor. And then we can either image these nanoparticles by their optical or other properties. For example, we can image them by fluorescence properties. And we can also use these nanoparticles as sensitizers of some therapies. For example, some nanoparticles can generate singlet oxygen or heat under external stimuli, which could be laser radiation or radio frequency radiation. And then we can, like that, heat for example, we can make chemical reaction, initiate chemical reactions, like, for example, the generation of singlet oxygen, which kills cancer cells. So, and these are the approaches of nanomedicine. But what is also important, one of very interesting approaches, this is the use of nanomaterials as transporters or carriers of radionuclides, which could be diagnostic and also therapeutic. And this is one of main, how to say, fields of our research. So we want to use nanoparticles as a carriers of radionuclides. In this case, we can load them with a lot of material, I mean radioactive material. And for example, if they come to the area of tumor, we can image this radionuclide. It could be, for example, gallium-68. We can image it by positron emission tomography easily. So, and then for therapy, we can also use them as a carriers. And like that, we can bring a lot of radionuclide to the region of tumor. And then, so these are normally short-living radionuclides. And then finally, if the carrier is safe, so we want to have safe nanoparticles, I mean, ideally biodegradable, which will then dissolve and go out from the body, so without any side effects. And this is one of key fields of our research. So basically what we want to do, we want to develop safe nanotheranostics. So the idea is that we produce nanomaterials by very clean methods like laser ablation. For example, it could be silicon nanoparticles, which are not only completely biocompatible with biological systems, they're also biodegradable. So within several days, they just dissolve and go out. So no side effects. And finally, we want to initiate some imaging or therapeutic functionality, and then we want to excrete them completely from the body. And then one of main fields, this is the marriage of nanotechnology and nuclear medicine. So here we use them as carriers or transport vehicles of some important radionuclides. So as I said, gallium-68 is good for PET, positron emission tomography. And for example, rhenium-188 is very good as a safe, relatively safe generator type radionuclide for therapy. And as an example, we recently published a paper in collaboration with the Radiology Center from Obninsk, so with the involvement of its directors, Sergei Ivanov and Andrei Kaprin, and the key person is Vasily Petriev there. So we showed the opportunity of using silicon nanoparticles as carriers of rhenium radionuclide. So this is a generator type radionuclide. So you don't need a reactor. So there is a small box, you can buy it from Rosatom, and you can have more than 1,000 doses. So just no reactor is needed. So then what we did, we just covered silicon nanoparticles by polyethylene glycol, which makes them invisible for the immune system. And then we attached rhenium-188. And as you can see, so here you can see by different colors, you can see the pharmacokinetic of this rhenium, which is linked to silicon nanoparticles. And by blue, you can see free rhenium. And it's clear that, for example, under intravenous administration, so we have a good circulation in all organs. But if we don't have silicon nanoparticles, just they all concentrate in the thyroid gland, which is typical for this radionuclide. So by just using these nanoparticles, we completely change the pharmacokinetics of this radionuclide. And then we had a very good retention of this radionuclide in tumor. So as you can see by this light blue, so there was a very good retention in the tumor if there is no nanoparticles. So they just go out, this radionuclide. And then finally, based on this carrier, we achieved a significant therapeutic effect. So with different doses of radiation. So it's, we believe this is a very promising field. We called it safe nuclear medicine. So this is we suppose that this could be a new direction. So we used a safe carrier. Then as another direction, another nice material, it could be samarium nanoparticles. Here we talk about their production by laser method. So you can see how nice are nanoparticles of enriched samarium. Then we want to irradiate them and use as agents to once again treat tumors. These both radionuclides, they are beta emitters, so they generate positrons. And normally how they destroy, so these are short-living radionuclides. They live normally, let's say, a couple of days for both. But what is important, when they generate beta radiation, it kills DNAs of rapidly proliferating cells, which are normally cancer cells. So other cells, they still are intact. So this is the whole idea. So our, how to say, new approach is the use of these new safe materials for nuclear nanomedicine. And then we also want to use the same materials as you know, sensitizers for some therapies, like for example, neutron therapy. So we want to use them as local absorbers of neutron radiation to initiate therapeutic function. The same about X-ray radiation. So this exciting project. So that's why we would like to see the presentation of Alexey Lipengots, who is a big specialist in this field, and our other, I mean, the other important speakers of this event. So just we want also their opinion on our approaches. are you right or not? So just that's what I wanted to say today. And please, how to say, thank you for your attention, first of all, and thank you to be with us. Okay, thank you.